Something is wrong with the comet from another star. It's not behaving like anything we've ever seen before. China's Mars orbiter, Tianwen-1, just sent back images that defy all expectations. After losing more than 13% of its total mass while passing the Sun, 3I Atlas should have a spectacular, streaming tail, billions of tons of gas and dust, illuminated by sunlight, stretching millions of kilometers into space. Instead, what we see is just a faint, compact sphere of light. No tail, no debris, just silence where there should be chaos. This isn't a glitch or a data error. It's been confirmed by multiple observatories, and the numbers tell a story that shouldn't exist. 3I Atlas, the third interstellar object ever detected, has now shown 10 separate anomalies, 10 independent behaviors that break the rules of everything we know about comets. Each one alone could be dismissed as coincidence or observational error, but together, the probability that all 10 could appear in the same object naturally drops below 1 in 10,000. Something about this visitor is profoundly wrong or profoundly new. October 3rd, 2025. While most of Earth was focused elsewhere, a spacecraft orbiting Mars turned its instruments toward a dim, fast-moving dot. Tianwen-1, launched by the China National Space Administration, had completed its primary mission years ago. But when data from Earth hinted that an interstellar comet was passing close to the red planet's orbit, mission controllers reprogrammed the probe's high-resolution cameras. They took a risk, and it worked. What they captured is now considered humanity's closest look yet at an interstellar visitor. The object was moving at 58 kilometers per second relative to the Sun. That's about 129,000 miles per hour. At that speed, you could circle Earth in 18 minutes. Yet, the comet itself is tiny by cosmic standards, only about 5.5 kilometers wide, roughly the width of Manhattan from river to river. When Tianwen-1 took its photos, the object was 18 million miles away. Think about that. A spacecraft built to photograph Martian landscapes had to refocus across 30 million kilometers of space to track something smaller than a city, darker than asphalt, and moving faster than anything natural we've ever recorded. It was like trying to photograph a fly buzzing across a football field from another stadium. The feat required precision, timing, and luck. And the fact that it succeeded makes these images historic. The Chinese National Space Administration didn't even announce the attempt until after the data was safely transmitted back to Earth. On November 5th, 2025, they released the images. A series of black and white frames showing a blurry, glowing sphere surrounded by a diffuse halo. They called it an important technical milestone, a test run for future deep space missions. But what they didn't emphasize was what makes these images extraordinary. This was the closest any human spacecraft has ever been to 3I Atlas. Closer than Hubble, closer than James Webb, closer than any telescope on or near Earth will ever get. At the same time, the European Space Agency's Mars Express and the Trace Gas Orbiter also caught glimpses of the comet as it passed near Mars. But Tianwen-1 delivered the sharpest results. And within those blurry details lies something strange, not what they found, but what they didn't. The absence of a tail. Here's how it should work. When a comet approaches the Sun, it heats up. Frozen gases trapped for billions of years turn to vapor, blasting outward under solar radiation pressure and creating the glowing tails we're familiar with. The closer the approach, the stronger the effect. It's one of the most reliable laws of comet behavior. 3I Atlas passed perihelion, the closest point to the Sun, on October 30th, 2025, at just 0.9 astronomical units, closer than Earth, and at times, even Venus. According to NASA's Jet Propulsion Laboratory, its orbit showed unmistakable signs of non-gravitational acceleration. Something was pushing it beyond the pull of gravity. The data was precise. A radial acceleration of 1.1 times 10 to the power of -6 AU per day squared, pushing it directly away from the sun, and a transverse acceleration of 3.7 times 10 to the power of -7 AU per day squared, sideways to the sun's direction. Those are not guesses, they're measurements. And the math is clear. To generate that much acceleration through outgassing alone, the comet must have lost at least 13% of its total mass at perihelion. For a 30 billion ton object, that's about 4 billion tons of material blown into space in just a few days. 4 billion tons. That's more mass than Mount Everest. And yet, despite that massive loss, there's no visible tail, no dust, no gas stream, nothing. Basic physics tells us that much material should create a spectacular blazing display. Instead, the images from November 5th show only a faint, fuzzy ball of light. 2 independent observatories confirm this: the Virtual Telescope Project in Italy and the R-Naves Observatory in Spain. Their photos, taken the same day, show the same thing: a compact sphere with no distinct tail. In both, the direction of the sun and anti-sun vectors are marked. That's where the tail should be. That's where 4 billion tons of vaporized material should be stretching into space. It isn't there. Compare it to Comet Lemon, observed just 2 days earlier from the same telescope. Lemon's tail blazes outward, perfectly aligned away from the sun, exactly as expected. It looks like a comet should look. ATLAS doesn't. So what's going on? Scientists are proposing explanations, but none fit neatly. Maybe most of the material ejected was gas, not dust, making the tail too faint to detect visually. Maybe the viewing geometry fooled us and we're seeing the tail edge on. Maybe the mass loss calculations are slightly off and less material was released than we think. Each idea sounds reasonable on its own, but together they start to feel like excuses. Because when multiple coincidences are required to make the data fit, when too many maybes pile up, that's when scientists start paying attention. Something is wrong with the model. And this isn't the only mystery. The missing tail is just one of 10 anomalies that make 3I Atlas unlike anything we've seen before. Each of the others breaks a different rule of celestial mechanics, chemistry, or probability. And when you list them all together, the odds of them coexisting in one natural object drop to nearly 0. Anomaly 1, its trajectory. When astronomers first plotted its orbit back in July 2025, they expected a random angle through the solar system. Interstellar objects come from all directions. But 3I, Atlas, was different. Its path was aligned within 5 degrees of the ecliptic plane, the flat disk where all the planets orbit the Sunday. That alignment might sound trivial, but it's not. Objects from outside our solar system should arrive from random orientations, up, down, or diagonal, relative to our orbital plane. There's no reason for them to match the exact plane where Earth, Mars, and Jupiter travel. Yet Atlas does, and its motion is retrograde. It moves opposite to the direction of the planets, but within the same narrow band of space. The probability of that alignment happening by chance? Roughly 1 in 500. Anomaly 2, the sunward jet. During July and August, telescopes observed something unprecedented. A stream of material shooting toward the sun, not away from it. Physics says that shouldn't happen. Solar radiation pressure pushes gas and dust outward, forming the tail. It's like trying to blow smoke into a fan. And yet, the data from multiple observatories confirmed that 3I Atlas was ejecting material against the solar wind. Astronomers considered whether this was an illusion, an anti-tail effect caused by perspective. But after analyzing the viewing angles and running the geometry models, they concluded it was real. Something was propelling matter toward the sun in direct defiance of basic radiation physics. No known comet behaves this way. Anomaly 3, its mass-speed paradox. The object's nucleus is 5 to 6 kilometers wide, weighing about 30 billion tons. That's 1,000,000 times heavier than Oumuamua and 1,000 times heavier than Borisov, the previous interstellar visitor. Yet 3I Atlas is also moving faster than either. In interstellar space, that combination large and fast is statistically almost impossible. Big objects are rarer than small ones, and high-velocity ejections require immense energy. The chance of detecting something that is both huge and fast is less than 1 in 1,000. But that's exactly what 3I Atlas is. And that's only the beginning. The anomalies keep stacking, each one more improbable than the last, each one demanding an explanation that doesn't quite exist. Anomaly 4, the planetary encounters and timing. 3. I-Atlas didn't just pass through the solar system randomly. Its route looked like a carefully plotted tour. In September, it swept past Mars, coming within tens of millions of kilometers, close enough for European orbiters to get a perfect look. Then it crossed the orbit of Venus and later brushed near Jupiter's domain. Every pass occurred while spacecraft were active, positioned to observe. None of the encounters were close enough to alter its course, but each was close enough to make detection possible. And then, during its brightest and most active phase, perihelion, on October 30th, it vanished behind the sun, perfectly hidden from every ground-based telescope on Earth. It's as if the object followed a path, designed to be visible to our machines, but invisible to our eyes. The probability of this natural timing, down to the geometry of the alignments, is vanishingly small. 5 in 100,000. Coincidence, perhaps, or choreography. Anomaly 5, composition. Spectroscopic readings changed everything. Most comets show a familiar fingerprint, water vapor, carbon compounds, traces of iron and nickel. But 3I, Atlas, flipped the pattern upside down. Its spectrum revealed more nickel than iron, an inversion never seen in natural comets. The nickel to iron ratio resembled engineered metal alloys used in spacecraft and heat-resistant structures, not icy rocks born in distant star systems. Even stranger was the ratio of nickel to cyanide, which was thousands of times higher than any comet on record. Orders of magnitude different. The chemical makeup didn't just deviate, it broke the chart. Anomaly 6, the missing water. Typical comets are 70–80% ice by mass. 3I Atlas is only 4%. That's practically dry. It behaves more like an asteroid with a thin frost than a comet. A dry body shouldn't produce outgassing strong enough to accelerate itself measurably. Yet we've recorded just that non-gravitational acceleration equivalent to 4 billion tons of expelled material, without any visible vapor or ice. It's a contradiction so sharp that even conservative researchers have begun calling it the dry comet paradox. Anomaly 7, extreme negative polarization. When light reflects off particles, its electric fields align in specific directions, a property called polarization. Every comet ever studied fits neatly into existing polarization models. But the light from 3I Atlas doesn't. It's inverted, far beyond any predicted values. No laboratory dust simulation reproduces this pattern. The polarization is so unusual that data analysts double-checked their instruments for calibration errors. None were found. The light is genuinely polarized in a way we can't explain. Anomaly 8, its point of origin. In 1977, a radio telescope at Ohio State University detected a 72-second signal from the direction of Sagittarius. The famous "wow" signal, never repeated, never explained. 3I, Atlas, entered the solar system from nearly the same part of the sky, within 9 degrees of that mysterious coordinate. Statistically, the overlap is small but not impossible, less than 1%. Yet in a story already filled with improbabilities, it's one more whisper of coincidence that feels heavier than chance. Anomaly 9, the brightness surge. Near perihelion, 3I, Atlas brightened faster than any comet on record. The change was not gradual, but explosive. Over a few hours, its magnitude increased beyond all models, and its color shifted toward blue, bluer than sunlight itself. Comets usually appear yellow-white, their light diffused by dust. Blue means something else, emission rather than reflection, possibly ionized particles or metallic radiation. Whatever was happening on that surface, it wasn't typical outgassing. And finally, Anomaly 10, the missing tail, the most visual contradiction of all. The math proves that massive ejection occurred, yet no trace remains. No visible tail, no gas spectrum, no fragments. It's as if billions of tons of matter simply vanished. Individually, each anomaly might be dismissed. Together, they form a pattern that forces uncomfortable questions. Harvard astrophysicist Avi Loeb has been among the few willing to voice them publicly. His view is cautious. He isn't declaring 3I Atlas an alien probe, but he argues that dismissing the possibility outright would be unscientific. When 10 independent anomalies cluster in one object, the correct response isn't ridicule, it's investigation. Loeb's position is simple. Extraordinary data deserves serious attention. Critics accuse him of sensationalism, but his approach is rigorous. He reminds us that skepticism should apply equally to extraordinary claims and to the claim that nothing unusual is happening. The data, he says, is what it is. And the data is bizarre. So what could 3I Atlas be? The conservative view holds that it's natural a comet from another star system formed under exotic conditions. Perhaps its parent system was hotter, drier, and richer in nickel. Perhaps the strange polarization and blue light result from chemical compounds we've never encountered before. Maybe we're simply seeing a rare but natural combination of factors that happen to cluster in one case. Statistically unlikely, yes, but in a universe of billions of stars, rare things still happen. The alternative view is harder to voice, but impossible to ignore. What if 3I Atlas is not entirely natural? Not a functioning spacecraft in the science fiction sense, but a construct, an artifact, built or modified long ago by intelligence unknown. Its composition metallic, dry, durable, would make sense for something designed to survive eons of travel between stars. Its motion aligned with planetary planes, timed to avoid Earth-based visibility, could be the result of deliberate trajectory planning. Its missing tail might not be a mystery at all if the acceleration isn't from outgassing, but from an active mechanism invisible to our instruments. That idea remains speculation, but speculation is where discovery begins. To ask what if is not to abandon science, it's to extend it. Loeb argues that refusing to consider unconventional explanations when data defies convention is itself unscientific. If all we ever do, he says, is fit the universe into our existing boxes, we'll never notice when the universe builds a new one. Meanwhile, data continues to pour in. The Tianwen-1 images, blurry though they are, remain our closest photographs of 3I Atlas, closer than any telescope will ever get again. The Virtual Telescope Project and our Nave's observatory images back on Earth align perfectly with the Chinese data. Compact, featureless, lacking the familiar cometary tail. Across scientific forums, debates ignite daily. Is the acceleration real? Were the spectroscopic readings misinterpreted? Did dust grains mask the tail's presence, or was the tail never there to begin with? NASA, ESA, and CNSA have all published partial data sets, but most raw imagery is still under processing. Citizen astronomers scour the skies for post-perihelion glimpses, hoping to track its fading light before it disappears beyond Mars's orbit. Every observation matters, because by January 2026, 3I, Atlas, will be gone forever, ejected back into interstellar space at over 200,000 kilometers per hour. And yet, the object's departure feels less like an ending and more like a challenge. We've glimpsed something that defies categories. We can explain parts of it, but never the whole. The question lingers: if this isn't a normal comet, what is it? Imagine an ancient artifact adrift between stars, powered not by engines, but by time, crossing the galaxy for millions of years, dormant, eroded, half buried in its own dust, yet still intact. Imagine it passing near a young star system, where primitive beings have just invented telescopes capable of noticing its passing. To those beings, it would look like a comet, bright, moving, uninvited. They'd measure its speed, its brightness, its trajectory, and realize it doesn't quite behave like anything natural. They'd call it a mystery. They'd argue. They'd wonder. That's us, now. Humanity, standing on the shores of its own solar system, watching a visitor from elsewhere, trying to decide whether it's a rock, a relic, or something in between. The truth may be simple. 3I, Atlas could just be a hyper-dry interstellar fragment formed around a nickel-rich star, the product of chemistry foreign to our experience. But the deeper truth lies not in the answer, but in the act of asking. For the first time in history, we're collecting direct data from an object born in another system. It's our first tangible sample of the galaxy beyond the Sunday. And the fact that it breaks our models isn't a problem, it's an opportunity. Avi Loeb says that science advances not by ignoring anomalies, but by pursuing them. Every revolution in understanding, he writes, began with data that didn't fit. 3I, Atlas, doesn't fit. And that's why it matters. As it speeds away toward the darkness, its mysteries remain. Some may be solved by reanalyzing the Tianwen-1 imagery. Some may stay unsolved for decades. But whether natural or not, 3I Atlas has already changed us. It has forced us to look outward, to confront the possibility that the universe still hides phenomena we cannot yet imagine, and perhaps messages we don't yet know how to read. By November, the debate had become global. Every major observatory on Earth, from Chile's Atacama Desert to Hawaii's Mauna Kea, turned its instruments toward the fading speck of light racing away from the Sunday. What they found only deepened the mystery. 3I Atlas remained compact, brighter than predicted, and completely without a visible tail. The measurements confirmed it had undergone massive mass loss. Yet space around it was clean, no dust cloud, no gas stream, no fragments drifting behind. It was as if 4 billion tons of material had been erased from existence. NASA's Jet Propulsion Laboratory recalculated the orbit again, accounting for every known gravitational influence. The numbers still didn't fit. Non-gravitational acceleration persisted even as solar heating decreased. The comet seemed to be propelling itself ever so slightly in a direction that could not be explained by sunlight or gas pressure. There was no evidence of jets, yet something continued to push it away. The acceleration was faint but measurable, an invisible hand nudging a 30 billion ton object through the void. Across the Atlantic, Avi Loeb published a new analysis from Harvard. He calculated the combined probability of all 10 anomalies occurring together, less than 1 in 10,000. In his words, either this object is the most statistically unlucky comet in the universe, or our understanding of interstellar bodies is incomplete. His statement reignited a storm of controversy. Some scientists accused him of sensationalism, while others quietly admitted that the data didn't fit any existing model. Meanwhile, the public's fascination exploded. The Tianwen-1 images circulated across social media, the first close-ups of an interstellar visitor ever captured from another planet. Citizen astronomers created animations showing its projected path passing Mars, gliding by Earth's orbit in December, then racing toward Jupiter. For a few days, it became a shared global mystery, the kind of phenomenon that makes people look up at the sky and remember how small we are. By early December, 3I, Atlas, was moving beyond the orbit of Mars, but still within reach of large telescopes. Its brightness remained steady, defying expectations that it should fade quickly after perihelion. Radio observatories listened for emissions, none detected. Infrared sensors measured its heat, finding strange fluctuations inconsistent with simple cooling. It seemed to pulse faintly, as if releasing energy in waves. Nothing matched the behavior of ordinary comets. And then came a quieter moment. The frenzy slowed as scientists realized there might not be more data to collect, only more to interpret. The object was leaving, accelerating into the black. By December 19th, it would make its closest approach to Earth, still distant at 270 million kilometers, but visible enough for one last global observation campaign. After that, it would slip away forever. Another interstellar traveler returning to the darkness between stars. What lingered was not fear, but wonder. We had witnessed something extraordinary, an object that broke the rules, defied explanation, and reminded us that the universe is still full of surprises. Perhaps 3I. Atlas was only a rare natural fragment, born in conditions unlike any we know. Or perhaps it was something older, something made, something meant to be found. We can't yet say, but one truth stands clear. For a brief moment in 2025, humanity looked beyond its solar boundaries and saw a mystery that no telescope could fully capture. As the weeks pass, the faint light grows dimmer, the data sets grow thicker, and the arguments continue. Scientists will debate, papers will be written, theories will evolve. But somewhere, 3I, Atlas, keeps moving out of sight, out of reach, yet still part of our story. Because whatever it was, it made us look up, question, and wonder again. And maybe that, more than any conclusion, is what this interstellar visitor was meant to do.